Welcome back to SyntaxGrid. In our previous video, we broke down k-nearest neighbors, KNN from scratch, covering its definition, applications, examples, advantages, and disadvantages. But theory is just half the game. In this video, we're rolling up our sleeves and diving straight into the implementation of KNN in Python, while addressing some of the most common concerns about the algorithm. Let's get started. Key concepts covered in this video: data collection and exploration, understanding the dataset we're working with, data cleaning and manipulation, preparing the dataset for analysis, data preprocessing, feature selection and scaling for optimal performance, data visualization, exploring the dataset with visual insights, model training and implementation, hands-on KNN implementation, model evaluation and optimization, assessing and improving model performance. Step 1. Importing necessary libraries. Before we begin coding, we need to import essential libraries that will help us with data handling, NumPy-Pandas, visualization, matplotlib.pyplot, Seaborn, data splitting and preprocessing, train test split, standard scalar, model training and tuning, k-neighbors classifier, GridSearchCV, evaluation metrics, accuracy score, confusion matrix, classification report. These libraries will ensure a smooth workflow for implementing KNN efficiently. Step 2. Loading and exploring the dataset. We'll be using the famous iris dataset from sklearn datasets. It contains information about different species of flowers with features like petal and sepal dimensions. To get started, load the dataset using load_iris. Convert it into a pandas data frame. Add a target column to represent class labels. This step helps us understand what kind of data we are working with before training the model. Step 3. Data preprocessing. Before feeding data into our model, we need to split it into features, ECACs, and target labels. Why? This step is crucial because it separates input features from the classification labels. Step 4. Train test split. Now, we divide the dataset into 80% training data to train the model, 20% testing data to evaluate how well our model performs on unseen data. We use train test split to randomly split the dataset while maintaining class balance. Step 5. Feature scaling. Since KNN is a distance-based algorithm, feature scaling is extremely important to prevent larger values from dominating smaller ones. We use standard scalar to normalize the data, ensuring all features contribute equally to distance calculations. Fit transform is applied to training data. Transform is applied to test data using the same scaling parameters. This makes sure that our model makes fair comparisons between different feature values. Step 6. Implementing KNN. Now comes the exciting part, training our KNN model. Initialize the model, KNN =, k-neighbors classifier. Train the model, KNN fit x train scaled, y train. Make predictions, ypred =, KNN predict test scaled. Just like that, our first version of the KNN model is ready. But how well does it perform? Let's find out. Step 7. Model evaluation. To check if our KNN model is performing well, we use 3 key metrics. Accuracy score measures the overall correctness of predictions. Confusion matrix shows correct versus incorrect classifications. Classification report provides precision, recall, and F1 score. Higher accuracy means better performance, but we'll optimize it further in the next step. Step 8. Hyperparameter tuning using GridSearchCV. KNN has one critical hyperparameter, k, number of neighbors, which significantly affects its accuracy. We use GridSearchCV to find the best k value by testing different values from 1 to 20 and selecting the one with the highest accuracy. Steps. Define a range for an n neighbors 120. Use cross-validation CV = 5 for better reliability. Find the best k value automatically. This ensures that we are using the most optimal KNN model for our dataset. Step 9. Training the model with best k. Train the new model with best k. Predict on the test data. Compare the accuracy with the previous model. This step helps us fine-tune our model for the best possible performance. A confusion matrix is a great way to visually interpret our model's performance. We use Seaborn heat map to generate a color-coded matrix, making it easy to spot errors and correct classifications. A well-performing model will have high values along the diagonal, true positives, and low values elsewhere. Wrapping it up, in this video, we explored the iris dataset, pre-processed the data and applied feature scaling, implemented KNN from scratch, optimized K using GridSearchCV, evaluated performance, and visualized results. If you found this video helpful, make sure to like, comment, and subscribe to SyntaxGrid for more hands-on machine learning tutorials. Have any doubts or suggestions? Drop them in the comments below. See you in the next video.